Okay, this is actually take 2. I just recorded a, 20-minute video on your pink sheet right here, and as I was recording, after 20 minutes or so, the camera shut off and it said, or the video on my phone shut off and it said, camera failed. So it didn't record any of that, and I have drawn all over this handout for you during that. So now this retake is going to have to work with a handout that has writing all over it. Not exactly sure what happened. Maybe there's a time limit for the video on the phone. Maybe the storage capacity is not such that it can handle a 20-minute video. I don't know. But anyway, here we are in take 2. So what we're going to do is look at your handout, your pink sheet here, which summarizes all the reactions of carboxylic acids and carboxylic acid derivatives. So this doesn't cover every single carboxylic acid derivative. It covers most of them, and it covers the ones that have this general form here, and that is a carbonyl with some sort of a leaving group attached to that carbonyl. And so in a nitrile, this carbon right here is triple bonded to a nitrogen, so it looks a little bit different than this form. So we won't be talking about nitriles in this handout here. We'll just be talking about the ones that have this general form. And so the overall view that you should have of a carbonyl or of a carboxylic acid derivative is similar to the view that you have of an aldehyde or ketone, and that is that the carbon has a partial positive charge on it, and it will act as an electrophile. The difference between aldehyde and ketone and the carboxylic acid derivatives is that this bond here can break because we have a leaving group. The overview, if we look at the entire diagram here, is that we can interconvert a carboxylic acid with different acid derivatives, and I have written these in an order that has, as we go up, we go to higher energy, and we go to higher energy, increasing reactivity because we have improved a better leaving group. So let's take a quick look at the leaving groups here. Here we have a nitrogen, which is an electropositive element that can't handle negative charge very well, and it's a small element, and so it can't delocalize the negative charge very well. So if that leaves with a negative charge, it will be a strong base, and it'll be a poor leaving group. So amides, which are found in proteins, are much more stable than any of the other carboxylic acid derivatives. If we have an ester, the leaving group has a negative charge on oxygen, which is electronegative, and it can handle that electronegativity can help to handle that negative charge, but it's a small atom, and so that negative charge isn't going to be spread out, and so we still have a poor leaving group. In an anhydride, when the bond breaks, the negative charge is spread out by resonance over 2 oxygens, making it a better leaving group. And then if the electrons go on to a chlorine, which is third period, much bigger atom, then we have an electronegative atom, and we have a large atom, good leaving group because it can stabilize that negative charge. And halides are much more reactive, so reactive that you don't see them in nature because of any moisture around will react and convert the carboxylic acid chloride back into carboxylic acid by hydrolysis reaction adding water. And so that's true for all of these, actually, that they react with water. If the nucleophile is water, comes in, kicks out the leaving group, hydrolysis will convert this back to the carboxylic acid. The ester reacting with water will convert it into the carboxylic acid. The amide eventually reacting with water will convert it back to the carboxylic acid. Let's look at the overall mechanism, which is going to be the same for any of these conversions that you see in this whole diagram. The overall reaction of carboxylic acids and acid derivatives is an acyl substitution mechanism. Acyl group, you remember from Friedel-Crafts acylation, is a carbonyl with some sort of a hydrogen or string of carbons attached to it. So the overall reaction that we're looking at is a substitution because we're breaking a sigma bond and we are forming a new sigma bond. So that's a substitution reaction. But more importantly, we have two steps in this reaction, and every mechanism will have these two steps, even though it has may have other steps of protonation, deprotonation. It'll always go in this addition elimination order of mechanism. First thing that happens, nucleophile comes in, adds to the carbonyl carbon, breaks the pi bond just like it would in aldehyde or ketone, forming a tetrahedral intermediate. And then, different from an aldehyde or ketone, we have a leaving group on here, and so we can reform the pi bond and kick out the leaving group. If we kicked out the nucleophile, we just go back to where we were before, but if the reaction kicks out the leaving group, we formed a new carboxylic acid derivative. So addition elimination is the mechanism that is governing all of these reactions up here at the top. So I'm going to stop here and stop the video because it looks like it's still recording, and I will call this a success, and then I will pick up in a minute with the second installment.